An international group of researchers from Portugal, Germany and Poland is working together to find an answer to the long-standing problem of dark matter. Dark matter is a matter that doesn't emit light and is therefore invisible to our telescopes. An alternative approach is to study it through its gravitational interaction with visible matter. Dark matter constitutes approximately 85% of the total matter in the universe, accounting for more than 5 times as much as all ordinary matter. Despite many decades of studying the impact of dark matter on the galaxy formation process and large-scale structure, its nature still remains unknown. By utilizing the new growing fields of gravitational wave astronomy and multi-messenger astrophysics, a group of scientists considered neutron stars as the probes for dark matter. Neutron stars are the ultra-dense remnants left behind by the exploding massive stars at the end of their life, the supernova explosions. These stars are extremely dense, with 1 to 2 times the mass of our Sun compressed into the size of a city. Due to their extreme conditions, compact stars constitute an excellent cosmic laboratory for studying ultra-dense matter properties and dark matter.
This project aims at investigation of the effect of dark matter on compact star properties. Particularly, we are looking on the different astrophysical signatures, gravitational wave signatures of the presence of dark matter.
Is neutron stars. They are very special objects for 2 reasons. Because not only we are able to understand them in terms of stellar physics, but also some cases we can test their physics in the labs of CERN and other collision detectors. Now the main point is in this research project is try to use our knowledge and try to expand not only how neutron stars work, but also try to use as probes of new physics in the universe. Specifically, we try to understand how dark matter, one of the big questions in modern times, affects the evolution of the objects, if at all. And in that sense, the main goal of this kind of strategies will be to see if we are able to discover new features about dark matter, how they interact with standard objects and compact objects in general.
For me, neutron stars have also a philosophical aspect, and that's about relation of microscopic and macroscopic, gravity or quantum mechanics, because these objects are extremely interesting. They have 2 aspects simultaneously. Not many other systems in our universe have that. Therefore, I do what is called equation of state and theoretical support of microscopical dynamics of the systems. I find it extremely interesting because so many different aspects, extremely rich physics can be found there. So people from really different areas could learn a lot. Condensed matter, quantum chromodynamics, electromagnetism, and many more.
Dark matter is a big challenge for many years, from 1933, and one of the problems we have is actually we don't understand its nature. Now, it happens in modern physics. One fundamental aspect when you talk about particles is we try to understand in the very basic terms. Can we put the dark matter particle within the standard model, which means in the same periodic table that we use for the other fundamental elements? And if you do so, like electron or quarks and neutrinos, is dark matter of that kind. And for that goal, there are 2 kinds of strategies. From one side, physicists are trying to build new detectors and try literally to catch one of them in their detectors. In another approach, the one we are concerned, is to use stellar objects like compact stars, neutron stars specifically, to try to see signatures of these new particles in the universe.
There is also another really interesting point why these objects are extremely interesting. Recently, it was shown that they might work as hoovers, but hoovers for something which is really exotic, dark matter. And that's another direction of our activity. We're looking for mechanisms which might provide a significant amount of dark matter inside of neutron stars. And particular scenario we're working on also includes possibility of relatively fast thermalization of dark matter, which is all in all consistent with the hypothesis of the Bose-Einstein condensation of that type of matter.
Isolated neutron stars are not the only systems to study this phenomenon. Mergers of neutron stars also provide a novel, sensitive, indirect method of detection and constraining the dark matter properties. Binary neutron star systems emit gravitational waves when they undergo their inspirals and mergers. These gravitational waves travel through the cosmos with the speed of light and could be detected by the gravitational wave telescopes. The first detection of a binary neutron star merger, GW170817, was accompanied by the observation of electromagnetic signals, such as a short gamma-ray burst, GRB170817A, its synchrotron afterglow, and a thermal kilonova, AT2017 GFO. This observation has enabled scientists to make exciting breakthroughs in our understanding of compact stars and their merger dynamics. Gravitational wave astronomy and multi-messenger astrophysics became new tools for extracting information about the internal structure of neutron stars from gravitational waves and electromagnetic observations. Given that dark matter accounts for a large fraction of the total energy in the universe, it is crucial to understand the impact of dark matter on neutron star properties and whether this could lead to biases in the extracted data. Indeed, a sufficiently large dark matter fraction inside the star could cause detectable changes in the gravitational wave and electromagnetic signals.
An international team of researchers affiliated in Portugal, Germany and Poland searching for the probes of the presence of dark matter in the compact stars. Particularly, we are looking on the signatures of the dark matter in neutron star mergers, kilonova ejecta, as well as astrophysical observations.
In addition to the on-ground dark matter searches, astrophysical and cosmological observations provide the first indications that dark matter might be self-interacting.
We've been observing the Ballet cluster, which is composed by two different classes of galaxies which are merging now together, and from the observations we can obtain some constraints on the dark matter sector, self-interaction and the interaction with the baryonic matter.
What we found out is that the dark matter accumulated in the core of the compact star tends to compactify the core much more, and in the end we will have a smaller mass and smaller radius of the star, while the dark matter halo creates this cocoon of dark matter around the baryonic component, leading to increase of the total gravitational mass, while the visible radius remains the same, which corresponds to the baryonic radius of the star.
Thus, the dark matter structure in neutron star is a dark matter core or a dark matter halo embedding the whole neutron star. The whole component of the dark matter is going to modify the properties, the astrophysical properties of neutron stars, such as masses, radii, uniformabilities, and the mergers as well in case of a binary neutron star system.
The presence of dark matter in neutron stars could affect their thermal evolution. Either can contribute to a heating or a cooling mechanism of the star itself. In our study, we have looked to a non-interacting, non-annihilating fermionic gas of dark matter that is accumulated inside the core of the star, and this triggers a Dirac-Turka process at lower values of the mass. Imagine two stars. One has a baryonic component and the other one has a dark matter admixed component. We have shown for the stars with the same mass, the dark matter admixed one has a faster cooling than the baryonic component, and this could be a smoking gun signature of dark matter in compact stars.
So part of our project is also about the understanding of how the merger process changes when dark matter is present when two neutron stars collide. And to understand this, we have to do very complicated, large-scale numerical relativity simulations, which have to run on big supercomputers. So our work first is to change the code infrastructure to make these kind of simulations work, then find the right computer, run them, and then later on investigate how maybe dark matter can change the matter outflow, so electromagnetic counterparts like the kilonova or also the gamma-ray burst, and also how the gravitational wave signal is changed in the presence of dark matter.
So what we want to study are now binary neutron stars with dark matter, and we want to see what are the effects of dark matter on binary neutron stars. But now if you have also dark matter in the center, then the whole star becomes more compact because there's now more gravitational mass in the center, and then the deformation is actually reduced. And this change in deformation you might see in the waveforms, and eventually when they merge you have disk, but in the center the two dark matter cores they might still be unmerged and still rotate around each other, whereas the baryonic matter is already merged and is also rotating, but as a whole thing. And then maybe you see an imprint of the second merger peak between the two dark matter cores.
In our recent work, actually, we found that the amount of outflow materials massively reduced. So we see not an as bright counterpart as we had seen it for AT 2017 GFO, so it's an electromagnetic counterpart to GW 17817. And this would be a very clear smoking gun signal if we detect a gravitational wave signal, which on the other hand does not have a bright counterpart except for the thing that we actually would have expected. So we basically see a bright gravitational wave signal, large tidal probabilities, but on the other hand, small electromagnetic signals not as bright as we've seen it before.
On the other hand, the presence of a dark matter halo leads to a significant increase in the outermost radius that goes beyond the baryonic component, and an increase in stars' tidal deformability. In this scenario, the coalescence of a binary system occurs in two stages. First, the dark matter halos merge to create a common envelope. Second, in the cocoon of dark matter, the baryonic stars merge further on. In comparison to the dark matter distributed in the core, the halo configuration with the high probability leads to a long-lived hypermassive neutron star, preventing a collapse into a black hole.
The critical point is that every kind of merger can be different. So we can have different amount of dark matters in one merger process compared to another one, so we have to be very careful in analyzing our data, which means that also we have to be prepared for all the possibilities that arise there. This means we have to do a number of different simulations, consider different dark matter particles, but also have to consider different binary properties. Maybe the neutron stars are spinning, maybe the neutron stars have different masses, or it could also happen that we actually don't really know the underlying baryonic equation of state. This also will have a clear imprint in the outflow and a clear imprint in the gravitational wave signal. To understand all of these numerical relativity simulations are actually key points, they're critical, and therefore a huge amount of investment has to be taken actually to allow for these kind of simulations to make them possible.
And I would like to ask a question whether the observational properties, either from neutron star mass, radius or tidal deformity, can able to constrain the dark matter models or not. And what we found, if we fix or freeze the nuclear equation of state, then there might be some kind of correlation exists which can from the observational properties of the neutron stars, which can constrain a few of the dark matter model parameters. But if you mix the uncertainty of the nuclear USS, then it is very difficult to decouple the scenarios from this way. So this also tells us that we need to look for some other kind of probe in order to constrain the dark matter in the neutron stars.
In the future, we try to use our simulations also to develop new models. In other words, we try to understand how dark matter affects gravitational wave signals, so that we will have gravitational wave models to analyze future gravitational wave events, which actually are expected to happen over the next 1 or 2 years with the next gravitational wave observing run from LIGO, Virgo and Coimbra. And on the other hand, we also have a huge amount of increasing possibilities for electromagnetic signatures due to upgrades. Maybe the CTF or also the James Webb Telescope will help us to understand basically better the electromagnetic signatures.